We're going to talk at a high level, kind of machine learning and how it complements optimization. So as an expert in optimization, as probably most of you are on the phone, what we're not going to cover today is too much on the details or break any new grounds about optimization or Gurobi, but instead focus our efforts on all the many ways where using machine learning can help complement how you use optimization. And as a side, one of the things that I like to think about is that in 10 or 15 years from now, we're not going to think of machine learning as a new thing or a different thing. It'll just be one of the toolkits that people who are experts in optimization know and use on a daily basis to enhance their optimization modeling. And so this presentation here is going to be kind of an introduction to that and say, how should you be thinking about machine learning as it complements how you work on optimization problems? So the first thing I'm going to start with is a management overview of machine learning. And I like to use this to help explain what machine learning is to new users, also to highlight some cases and interests of why machine learning might be interesting. So the other thing that you like to think about with this is that machine learning is something that you want to be able to explain to your colleagues, the people who are making decisions, sort of why you're integrating this, why it's interesting, and some of the new things that you can do to open up some of the art of the possible in terms of breaking new ground. So the first thing, I'll just start at the basics. So where machine learning fits in, if we think about an analytics framework where we have prescriptive analytics down at the bottom where we're doing optimization or stochastic optimization, this is what we all know about. And then the other areas of analytics would be the descriptive analytics where you're reporting, or the predictive, which is where machine learning fits in. So we're going to focus a lot on, what is the machine learning? How does this work? What kind of benefits can it bring us? So the first thing I like to point out with machine learning is that it can span a wide range of different activities and different types of analysis. So it can be anything from relatively simple things on the left where Netflix or Amazon is making a recommendation to you, to everything on the far right where machine learning is actually helping automatic driving cars, autonomous driving cars. So machine learning sort of fits this whole spectrum. So when people hear about it, they either tend to think of sort of one or the other. And what I want to do, and I think you should do with the people that you work with too, is sort of paint the broad picture. The machine learning is just a tool. It can be used for quick and simple analysis. It can be used in more sophisticated ways to do very high-tech kinds of things. And then the other thing I like to point out with machine learning is why is it better? So what does it do that's different, and what new ground does it break? And this is a great example of how you can think about it. So in this example, we're trying to predict whether one of these circles will be orange or will be blue. And if I look at traditional methods like simple regression, I'm just drawing a line through this group of dots, and I'm going to say, well, everything above the line I'm going to guess is going to be an orange circle, and everything below the line I'm going to guess is going to be a blue circle. And you can see that the simple regression is not bad. So most of the stuff above the line is orange and most of the stuff below is blue. But what machine learning can do is apply different types of algorithms to draw better boundaries. And so here in this case, with the same set of data, a machine learning algorithm can figure out what's a more sophisticated boundary between the blue and the orange. And now you see everything above the line, again, is predicted orange, below blue, and you see it gets a lot better. And what it did was the machine learning algorithm could figure out this peninsula of orange dots that kind of juts into the blue area and say, well, this is actually a different pattern, and let's spell that out. Now, you also notice that with this boundary here, we're probably not going to be able to come up with the same statistics that we had before with the simple regression. So we'll have to have other methods for testing how well this works. And Sam will talk about some of these in detail as he goes into a section. But I think this is a nice intuitive way to think about why does machine learning better and what can it do different? And it can help tease out patterns that might not be so obvious at first. The second thing I like to cover and talk about a little bit is, what do we mean by the word learning? So it's kind of a funny word to use in conjunction with machines. So what does it mean? What is the computer actually doing? How's it actually learning? Does it learn like we all learn, or does it learn in some different way? It actually turns out it's a fairly technical definition of learning. And I like to contrast it with what it's not. So what it's not is it's not a rules-based system. So let's take an example. So let's look at these potato chips on the left and try to figure out which one of these is high quality and which one is low quality. So which one is good and which one is bad. So if I take a rules-based approach, what I do is I get a bunch of quality control engineers into a room and I have them define the equations which define a bad potato chip. So they're writing out all these different equations about what makes a potato chip good and bad, and they have to write out all these different use cases. And the problem with this, and why rules-based systems have tended to fail and don't scale that well, is there's just too many rules. So there's too many ways that a chip could be bad. It's not very flexible. So if you introduce a new type of chip, you have to get the whole team back in together, rewrite the rules again. So it's not a great system. It's not a very scalable system. So instead, this is where learning came from, is that folks realized that if I could somehow get the computer to recognize these patterns without having me to provide the detail, I could be a lot more efficient and scale a lot better. So for example, in this case, what I would provide is I'd provide the algorithm set of pictures of all the potato chips with just a label that says this one's good, this one's bad, and I wouldn't provide anything else. And then I'll let the algorithms figure out what were the patterns that led to a good chip or a bad chip. And so in this case, this is how we're using the term learning. It's we're feeding the algorithm some set of information, and we're letting it figure out what the patterns are and what the rules are. So that's what we're doing with learning. Then we'll get a little more technical here, break it up into a couple groups. The first group of learning is what folks like to call supervised learning, which is like the example I gave you before. And supervised learning is where we have labels for the data. So we say this is a good chip and this is a bad chip, and we let the algorithm figure out the pattern. The other type of learning is unsupervised learning, and this is type of learning where I just provide the computer with, say, the chips or another data set, and I say, tell me what the patterns are. So you tell me what patterns you see emerge, and then I'll see if there's some value in those patterns, and that's unsupervised learning. So we'll do a little look at both of these. Let's start with unsupervised learning. So in the US, several presidential elections ago, I can't remember which one, all of a sudden, everyone in the US and the media was talking about this term, soccer moms. And so they used this term to define a portion of the population, soccer moms, who were, women with young children who lived out in the suburbs, and maybe their kids were into soccer. But where did this come from? The place this came from is it came from unsupervised learning. So at some point, someone decided to do an analysis of all the demographic data or voter data and asked the algorithm to come back with a pattern. They came back with this pattern, and when you looked in the pattern, this is where you found out, oh, it's women with young children, it's women who live in the suburbs, etc. And then, the computer didn't say, hey, we have this group soccer mom. Someone came up with the clever term, but the idea was there was this group of people who were very similar across the country who weren't identified before, and because of the unsupervised algorithm, they were now identified and they could be marketed to, spoken to as a group. And I think the reason the term stuck was because it was actually a real group that had kind of been hidden under the radar because it couldn't be seen with normal techniques. Now, another way to look at this, bringing this back to business, is this example from Best Buy. So Best Buy published some information about how they did this. So this was their version of soccer moms. And Best Buy is a store here in the US focused on electronic goods. And what they did is, instead of defining their customers in standard ways, like the age of their customer or where they lived or what their income might be, they looked at customers across different parameters in terms of what types of products people might like to buy, when they like to buy. Do people like to buy when a version 1 is released, or do they like to wait until version 10 is released? They also wanted to know, do people use credit or buy with cash? Do people respond to emails? Do they like to come into the store? All these kind of parameters, and came up with a new set of groups where they could now more finely target their efforts. And I think this is interesting from an optimization point of view, because now Best Buy, has to budget marketing, and now knowing these different groups, they can figure out which groups do I actually budget to, and how do I set up my optimization model so I can appropriately budget to the right individuals and the right people. How do I lay out my stores in the right way, thinking about these groups. So this is one way to get better input into our optimization models as we think about how do we define these different groups and what are the actual groups of people that we're interested in. Now let's move over to the supervised learning. And this example came from the first webinar that you heard in this series, so the last one. And Pete talked a lot about this and gave a nice example where forecasting was complementing optimization. So the idea is that I can use forecasting and feed that into my optimization model as an input parameter. And here, what I'd like to talk about is, as you think about the forecasting, one of the interesting things here, and it was discussed in the last webinar as well, is the idea of this feature engineering, where you work with external data. So I think you're going to hear the term feature engineering, and the idea here is I have lots of potential parameters that I could input into the model. And the question is, which ones do I actually input into the model? And so forecasting, we can have anything from special events to demographics to weather to contracts to, is this particular retail location close to other competitors or not, and so on. And so this is the exercise of feature engineering. And I think this is where a lot of the creative effort comes into machine learning. And one of the takeaways for you guys is to think about what creative new data sets could I bring into my models to make them better? So how can I make my optimization models better with additional external features? And so I may bring in the features, use some machine learning algorithm, that eventually feeds my optimization model. Another good example is this one from predicting truck prices in the trucking market. So in the trucking market, we have two different groups. You have the shippers. So these are companies that want to ship a product from point A to point B. And then you have the carriers, which are the trucking companies and the trucks that move that product. And this is results of work from a particular academic paper that was published and based on a project that we did with that client. And in this case, the client was the broker. So they were the person in the middle between the shipper and the carriers, trying to negotiate what's the right price for each. And what you see here in this curve is two curves. So look at the dark curve that starts down at 0 on the y-axis and goes up to 1 on the y-axis. So this is the carrier curve. So this is the curve for the trucking company. And you can see that their acceptance rate gets higher and higher as the cost per mile. So that the x-axis there is here, US example, where it's the cost per mile. So you basically get more money the further, or how much money do you get per mile as you go to the right. And you can see the trucking company is very happy to accept those loads and those moves the further you move to the right, which is intuitive. And the same thing for the light gray line, which starts out high. So if you have a very low cost per mile, so it's very cheap to move that, the shipper was very likely to accept that. And so in this example, we have these two curves, which represent these two different markets. And we use some machine learning techniques and lots of feature engineering to figure out what each of these curves looks like. And so now we have a curve for the shipper and the carrier. And you can think of the brokers in the middle trying to figure out, when a shipper calls, what price should I quote, knowing, how likely is the carrier to accept, or how likely is the shipper to accept, and then also if I have that price, am I likely to find a truck that's willing to make that move? And then what's interesting from an optimization community point of view is that in the middle here, there's a small optimization model that needs to run that says, given these probabilities and given my objective, what price should I quote when I'm on the phone to maximize my revenue, maximize my profit, etc. The other aspect I wanted to touch on with machine learning is this idea of how do machines appear to be getting, quote unquote, smarter over time. And one of the ways should think about this is that the addition of data can help me do better with the predictions. And so this article I'm showing here from Google is one that kind of kicked it off, this unreasonable effectiveness of data. Had a lot of their effectiveness here was in the field of translation. So they thought, people have been working on language translation for a long time, and the algorithms were sort of stuck, and they weren't very useful. And what happened was Google figured out that if they could collect more and more data, so a couple orders of magnitude more data, the algorithms suddenly got a lot better. The same algorithms were performing much better, and this is what they call the unreasonable effectiveness of data. So this is how you can think about machines appearing to get smarter. As I can feed more and more data in, the algorithms tend to get better and better. Let's come back to our chip example. And how do we find a bad potato chip and kind of tie that to this? I thought this was an interesting story about the use of predictive models. So in the manufacture of chips, these things come off the production line and enter into a conveyor, and this conveyor is very fast moving. And what happens is a picture is taken of each of the chips, and the system remembers where that chip is relative to the others on the conveyor. Then there's a machine learning algorithm that's applied, probably a k-nearest neighbor type of algorithm, where it compares a particular chip to the database of good and bad chips and figures out, is this new chip good or bad? If it's bad, the chips all pass on the conveyor line, they all pass over a little gap in the conveyor line. The chips are moving so fast that physics will take every chip over that gap. But what happens is there's a bunch of air nozzles over the gap, and the bad chip, once it's identified, the system knows where it is exactly on the conveyor belt, and as soon as it passes over that little gap, a puff of air comes out and the bad chip is blown away. So I think a nice implementation of predictive models. But also, this is an example of where if I have more and more data, the algorithms get better and better. So as I get a bigger database of good and bad chips, I'm now making much better decisions as those chips move across the gap of which ones I keep and which ones I get rid of. All right, let's focus a little bit on how machine learning can complement optimization, get a little more specific now that we've gone through the general. And then after my section, I'm going to turn it over to Sam, and he's going to get into some of the detail of the Python code about how it works as he walks through a case. So I think you want to think about a simple modeling framework where I prep data, and when I prep the data, you can think of this as I can enhance this preparation with machine learning, and there's ways to enhance it with optimization as well, as you probably likely know. Then I prep the parameters, so I'll figure out what kind of parameters go into this, and then I do the modeling. And each of these steps can be improved, or you can actually use machine learning or an optimization model. But the other thing I wanted to point out is that, as you know, when you build your optimization models, you can build sophisticated models where you may run a linear program that then feeds an integer program that then comes back to another linear program. So there's steps 3 and 4. I can iterate between my different models. So those are techniques that we all know from optimization. But I also want you to think that I can insert machine learning into this step as well. Like I may run an optimization model, a nice mixed integer program. That might feed a machine learning algorithm that gives me some information, then that has me kick off another mixed integer program that helps me answer the business question. And I want you to think that machine learning is just another tool that you can use. So just as linear programming is a tool you can use to help solve your integer programs, machine learning is again another tool that we can use to help solve our optimization problems. So one quick way is I think about the data prep and how I work with the data. At a high level, I can think of kind of 2 things I can do. One, I can compress the number of rows that I have. So if you think about clustering here, I can think about how do I reduce the number of maybe customers that I'm shipping to. So instead of looking at each individual customer, if I'm Amazon, I'm not going to build a model for each customer. I'm going to somehow group my customers by their velocity, how frequently they order, etc. And that can reduce the number of rows. On the right, I can reduce the number of columns. This is factor analysis. So as I'm doing an analysis, there may be 100, there may be 1,000 variables that I think may be interesting for my model. I don't know which one is interesting, and I use factor analysis, and here principal component analysis is one example to compress the number of columns that I have so that I can have fewer features that I need to analyze. This is an example of the clustering. So I can actually do clustering 2 ways. One is if I have one single dimension, which turns out to be a negative of this approach, I can use an optimization model. So I can come up with an exact answer that says, well, let's cluster our customers just by their location, and I can run an optimization model by that. If on the right, I want to cluster my customers by more than just their location, maybe I want to cluster it by distance plus something like how frequently they order, or maybe the types of products they order, because that will make my optimization model more sophisticated. There's machine learning techniques for this, like k-means clustering, which Sam will talk about. And this helps me group my clusters across multiple features. And the negative, it might not be optimal, but Mike Trick has written a blog post about this and says in general, the k-means algorithm tends to work pretty well. All right, let's talk about automated parameters. So this is another way that we can help our optimization models. So one of the things that I think about when I build my optimization models, and one of the, I guess, downsides is that as optimization experts, we're kind of relying on others to provide us the input data. So, what's the input data that I need to feed into the model to make this thing work? And if I can automate this and use machine learning to do this, I can actually scale a lot better. So one example that we worked on had to do with seasonality, trying to figure out, when the season started and when it ended. And I think what was interesting about this is that the business knew that in peak season, I had different parameters that I wanted to look at. So I had different ways I wanted to look at my data and different decisions I wanted to make. And I also had different input data, like lead time might vary over time. And so by using machine learning techniques, we could actually automatically help figure out, when did the season start and when did it end? So in the past, I would have had to rely on someone to tell me for each product, when did it start and end? And this is like a rules-based system where you can see where this could easily fail and not scale. Like maybe I get people to do the exercise once, and 3 years from now, those parameters have become out of date. Instead, we can use some type of algorithm to figure out and tease out these trends and figure out for each of these different products, when does the season really start and when does it not? Here in this case, we use a Gaussian mixture model to actually separate the peak from the non-peak. But a great way to think about how to scale your models with automated parameters. And it's like one less thing that you need to ask the users for in terms of input data. Coming back to the forecasting, another way to help scale it, we talked about this, using the feature engineering to combine my data that I have with the other features. We found some successful techniques in Ensemble, Random Forest, support vector machines. And just a little bit of data. So we did some analysis with a CPG company looking at how well did machine learning forecast relative to their ERP system. And what you can see on the left is that compared to the ERP system, for 78% of the products in the portfolio, the machine learning algorithms were able to come up with a better forecast. And on the right, you can see that that forecast was robust across lots of different products. So we didn't know if it was just applied to fast moving or some other category of products, but it worked for fast moving, it worked for the volatile, it worked for the different types of products in the portfolio. All right, let me introduce the case study, and then we'll dive into some of the Python code where it'll get a little more detailed, but you can kind of look under the hood to see how this works. And Sam will give you some good insight from a machine learning practitioner point of view of how to think about these different steps. So the case study is going to focus on a trucking company, and we're going to try to figure out how do we quote and predict the rates that we may pay. And this is a non-asset-based trucking company, so a trucking company that doesn't own the assets but is dealing in the market. So, and they need to understand and try to predict the rates because they need to quote these rates, give their agents guidance on what the rates might be. And what makes this problem ripe for machine learning is that there are thousands of lanes across the country. We have lots of different agents. There's lots of historical data. There's lots of features that we can look at. That's our setup for the case. And we're going to use the term freight bill and loads. And this refers to nothing more than all the detailed data between what's the information and the cost for historic moves when I moved a product from city A to city B. What was the cost? What was the time of year? What were some of the other factors there? And then I can use that data to make insights and guesses about the future. So these are some of the features that we hypothesized that said these may be important. So we said the agent may be important, the flow, the calendar, you know, the day of the week, the month of the year, this all may be important, the customer that I shipped to, the historical rate that we paid, etc. So these are the things that we thought were important or might be important, and the feature engineering helped us select and figure out which ones were important. So you can see the ones in green, they actually mattered more than the ones that turned out in red. This is not a universal statement. If I go to the next client and customer, it might be exactly the opposite. So I think about the modeling steps we're going to go through. So we're going to focus on the non-asset company. I'll talk a little bit about the asset in a second. So from the non-asset company point of view, we need to prepare the data. We need to aggregate it, and we can aggregate it with optimization or clustering. We need to calculate features for machine learning. We need to reduce the dimensions, or at least think about this. In this case, we actually don't need to do it in the simplified version that Sam did. In other cases we've worked on, we've had 3,000, 4,000 features, and we needed to do this so that we could actually run the models. And then we need to build and validate our predictive model. So you can see lots of steps up until the modeling. If this were an asset company, this step would all be sort of just the prep work, and then there would be a whole bunch of work on the asset side, building a nice optimization model to figure out, well, given all the historical prices and the market prices, how do I actually make sure that I can move my vehicles around from point A to point B and make sure they're positioned in the right place, and then use that linear programming model to help adjust the prices coming out of what you see on the left. So it'd be a whole nother case study on that, where the optimization model would be the primary one. Here, what we're going to show today is we're going to focus on just the machine learning part to prep this, which was good for the non-asset company, and think about this would be an input to the optimization model. All right, with that, I'm going to turn it over to Sam, and he's going to provide more details on how this works and lift up the hood a little bit.
Okay, so as Mike mentioned, one of the things that we're going to look at doing is using a clustering model to sort of segment our customers into markets so that we can have not only a more manageable problem, but also a richer feature set. To do that, what we're first going to do, whether we're going to structure this as a MIP or a clustering problem, is we need to have a distance matrix between all of our destinations. So rather than using the Habersign formula, which if you're not familiar with is a formula that involves a lot of like trigonometric functions for calculating distances on the surface of an ellipsoid. It's the proper way to calculate distances between 2 points on the Earth, but instead we'll use a projection called Earth-centered, Earth-fixed that allows us to transform our latitude-longitude pairs into X, Y, Z points, and we can then use Euclidean geometry to calculate the distance between them. This ends up being a lot faster. It's not as accurate, but for short distances, especially because we're looking at just points in the United States and part of Canada, it ends up being fairly accurate. Another point to keep in mind is that we're not using road distances to begin with, so we're already using a proxy, and this is just another proxy for that proxy. So we'll start off by loading our data. We're going to be using the pandas library throughout this demo here. This is a stripped down data set that we're showing just for the purpose of clustering. It's going to have just 4 columns. First is freight bill. As Mike mentioned, we can just think of freight bill as essentially being a contract between a shipper and a carrier to move a load from point A to point B for this price. Next, we have a date ID that maps to a specific day of the year, and along with a destination, latitude, and longitude. So we're first going to apply our projection from that function that we defined in the previous slide. Just a point of note here for people who are maybe kind of in the beginner to intermediate stage of using Python, there are 2 interesting functions that you can look at here. The first is the apply function that we apply to pandas data frame called clusterdf. What that allows us to do is literally apply a function across every row in the data frame. It's a much more efficient way of calculating transformations in the data. And the next is the zip function along with the star unzip operator that allows us to take that tuple that's returned from the conversion function and actually convert it into 3 columns rather than a column that has a tuple of 3 values. So you can see here how the data frame looks. We now have 3 new columns, the X, Y, and Z coordinates that we're going to use in a Euclidean space for calculating the distances between our points. So now we're going to load the k-means modeling object from the clustering module of the scikit-learn or sklearn library. So a few things to kind of go. There's only 2 lines of code here, but I think there's some points that are worth discussing, because as you sort of start to explore machine learning in Python, you'll certainly come across a scikit-learn library, and it's important to understand some of the arguments that we're passing to these models. So for feature engineering, our first value that we're going to pass is this n clusters equals 100 argument. Basically what that's saying is we want to get 100 distinct clusters, which in this case represent markets, from this algorithm. The idea here is that we, remember we're trying to do this for feature engineering, so we don't want to have too much sparsity, but we also want to make sure that we have, a more manageable problem size. Basically, if you can think about 2 suburbs that are of major cities, we may not have a lot of information about loads that traveled directly between those 2 suburbs, but we may have an idea of, generally what loads look like, characteristics of loads in the past and their associated rates from the whole metropolitan area. And so typically, as we're doing this geographic-based clustering, what we're going to end up with is sort of those metropolitan areas that are being, defined in a programmatic way rather than a manual way. The next argument that we pass is this n init equals 10. And, not just kind of given a little bit of background, knowing that we have sort of a broad range of knowledge bases on machine learning. So, if you're maybe more of a beginner, what this means is this is the number of initializations that the k-means algorithm will test. If you're unfamiliar with how the k-means algorithm works, basically a set of centers, which are called centroids, the center points in each cluster will be randomly assigned at the beginning of the algorithm. It's there are algorithms and heuristics for doing this somewhat intelligently, but there's still an element of randomness. The way it works is then it iteratively reassigns points to the closest centroid and then recalculates the centroid based on the new point assignments. So it'll basically do that until, over a certain number of iterations until the change in cluster assignment is fairly minimal. So knowing, what we know about optimization, we know that a process like this could possibly reach local minimums rather than finding a global minimum. So in an effort to find a more optimal value, we actually initialize this multiple times. So we'll look at 10 different random initializations, figure out where they reach their local or possibly global minimum, and then we will select the set of centroids that minimizes our error metric. In this case, what we're looking for is minimizing within cluster variation. Our final argument that we have here is this n jobs equals -1. So one of the nice things about, a lot of machine learning algorithms that, especially this scikit-learn library in Python takes advantage of is that many of them can be thought of as a combination of a lot of smaller models that can be computed in parallel. So if you're thinking about, as a simple example, these 10 different initializations, they actually are completely independent of one another. Because they're independent, they don't need to be run sequentially. Because they don't need to be run sequentially, we can obviously run them in parallel if we have that capability. Scikit-learn gives us that capability. So if we pass an n jobs parameter, it's basically telling us how many of these models do we want to calculate in parallel. We're limited by the way that scikit-learn works to the number of cores that we have available. So n jobs equals -1 is basically just saying as many cores as we have available, that's how many models we want to build in parallel. So, if that kind of explanation is either uninteresting or kind of going over your head, the entire point to think of is that if you pass n jobs equals -1, it's going to make your algorithm run as fast as it possibly can on your computer. Okay, with all of that, now we're going to actually use this model to fit and then assign our points to clusters. So again, there's, in the first two lines here, you see a model.fit and a model.predict. These are two common methods that every modeling object, or nearly every modeling object in scikit-learn will have. The fit method basically tunes the model to the data set that we pass it. In this case, that's our X, Y, Z coordinates. And the predict method is going to basically output a value assignment from the model for a given input data set. That could be, in this case, we have a category, our final column that was added here called cluster. In the case of a classification model, it could be a classification probability or a set of classification probabilities. Or in the case of a regression model, which you'll see later in this walkthrough, it could be an actual floating point value. And just a quick mention back to what Mike said earlier, this is also a case where, what we're going through is a data preparation step right now. We're choosing to show a machine learning based approach because this is a machine learning webinar, but we could have just as easily used a MIP to power the generation of the markets, right? And this is a fairly, straightforward sort of warehouse opening problem. The only difference is in the way that we structure the input data, where we can, instead of having to pass, say, 100,000 individual records, we can roll those records up and do a demand-weighted optimization. Okay, so here is the sort of output of our markets. You can see, as we mentioned, if you're familiar with some of the geography of the United States, you can tell that a lot of these clusters are centered around metropolitan areas. And that's, typically what we're going to see. But again, what this does is it allows us to automate this process rather than having to, say, choose some arbitrary separation like zip codes or postal codes or county state boundaries to create our markets. Okay, so now I'm going to talk for a little bit about a topic that Michael had mentioned, which was feature engineering. And so I think, this is something that I think is worth stressing on a little bit. It's a part of the machine learning predictive analytics process that's absolutely critical for the success of any model. So in this instance, we're looking at predicting a baseline rate per mile for a specific load based on some characteristics. As you can imagine, we have some characteristics about the load itself when it comes in, but we also kind of want to know some of the information about the environment in which that load is being introduced. So we're going to want to know things about the past, historical values at any given point in time throughout the process. So an example would be, we have an origin cluster and a destination cluster. How many loads have we seen between those in the last 15 days? How many loads have we seen terminating in the destination cluster that we're looking at in the last 15 days? We might want to know some information about the shipper themselves. We might want to know some information about the potential carriers that we'll be selling these loads to and what price we should be offering them. So there's a lot of information here where we'll want to be able to get historical data. And as you probably know, from having to prepare data for optimization problems, or maybe you have prepared data for machine learning problems, the data is rarely in this format. We'll typically need to do a fair amount of engineering at the beginning to prepare our data for an effective model. And so in this engagement, we spend a significant amount of time deriving and creating some complex features. Here, we're just going to walk through one simple example. So with that big preamble, while it's not necessary for this demo, I think a great way to kind of start off and just to sort of show how we would do it is creating a sort of feature master data frame that we'll use for tracking all of the features that we're going to go through and generate. So we start off by just getting all of the distinct freight bills that we have in our historical data set that we will use for modeling. So our next step is to join the data frame back on itself using the cluster column. What we'll get here is essentially a pairing, a tuple of every pair of freight bill numbers that existed in the same cluster. So you can see that what we'll do after that is we'll look to, if we're looking for, say, in this case, a count of the number of loads ending in a cluster in the last 15 days, what we're going to need to do is, after we perform this merge, which is similar to a join function if you're familiar with SQL, is we'll need to then go filter based on the date ID column. And so we'll see that in the next slide. But one point to make is that if you are familiar with SQL, you notice some inefficiency here, which is that ideally, if we were performing a join, we would, in the on clause, be specifying our filter, so we're not creating a bunch of unnecessary data. Unfortunately, that functionality is not present in Python. So if we had a very large data set, we probably would want to be outsourcing this operation to SQL or a SQL-like sort of language that allows us to not create all this unnecessary data. But for the purpose of this presentation, and for a lot of cases where we're only looking at, say, a few 100,000 records, this is a perfectly plausible approach. So our next step, we apply those two filters that we talked about. First is making sure that the second freight bill that was joined on is going to be at a date ID that is earlier than the reference freight bill number. And the second filter is then making sure that that date ID is going to be within 15 days of that reference number. Okay, so finally what we're going to do is we're going to use the pandas group by function, which allows us to perform different aggregation functions. In this case, we're going to do a count of all of the second freight bill numbers that ended up being within our relevant date range for the reference freight bill number. And then we're going to use a rename function to get that feature to have the name that we want it to be. In this case, loads end 15, meaning loads ending in this destination cluster within the last 15 days. Finally, our last step is to merge this data back into our reference data frame, always using a left join in this case, and then filling our null values with a 0. The reason we want to do this is because if we're going through this feature engineering, it may be the case that even though we've tried to avoid sparsity, we still may end up having markets that do not frequently ship to each other, or when we end up with more complex features, our data set may just be more sparse in general. So we want to make sure that we're not performing inner joins, or we'll quickly end up with a data set that has 0 records. We want to make sure that we're always performing a left join on that master feature data frame to ensure that we are keeping all of our historical freight bill records. Okay, so now let's fast forward a little bit. Say we've gone through generating all of our features. Our next step here is to divide our data set into 3 subsets for performing modeling. What we're going to do is divide into a train, a validation, and a test set. The idea here is that we're not going to try to build just one single model on a training data set and then see how it performs. What we want to do is we want to test a bunch of different parameter options with that model. So first, what we'll do is we will train the model on, say, 80 days worth of data, and then we will see how it performs based on some error metric on a validation set. Then we'll go back and retrain that model with a different set of parameters and see how that performs on the validation set. And what we'll do then is, after we've, say, done a grid search over all the parameters that were and all the models, different modeling algorithms that we're looking to test, what we'll do is we'll find the one that had the minimum error rate on the validation set, and then we'll retrain our model, including both the training and the validation set. And the reason we do that is we want to make sure we have the most recent data, since we're doing this with time-based splits. And then we'll actually see how that model performs in the test set. And the test set will be the true evaluation metric. So the validation set is really just there for the purpose of training and selecting our optimal parameters and optimal machine learning model. So if you're familiar with cross-validation, you may be familiar with something called k-fold cross-validation. What that basically means is that we sort of randomly split up our data set between training and validation, say 10 different times to produce an error metric. What we're doing here instead is we're suggesting a walk forward metric. In this case, what we're assuming is that over time, things in the market may evolve. And so what we would do in this case is, this is a single time period. We would then move, say, shift this window 20 days forward and perform the same measure. And we might do that 10 to 20 times and then sort of use an overall kind of error measure to determine how good our modeling technique was. Another good part of this approach is that it allows us to sort of simulate the way that this model would actually work in a production environment, making sure that we're only training and then testing, where the test set is always going to be data that's happening in the future with respect to the time period that was used to train the model. Okay, so one thing we're going to do here that we're going to show that's not really necessary on this data set is the idea of dimensionality reduction. So here in this sort of, we made a kind of dummy data set here where we generated just 72 features. And what we may want to do at some point is, in our sort of modeling careers, is do a dimensionality reduction. A case when this could actually crop up is if we have just way too many features, especially when we have way too many features with respect to the number of training examples that we have. So I think, a good example that pops in my head is Mike's potato chip example. So if we had, say, 128 by 128 pixel images of the potato chips in our database, that comes out to a feature vector if each pixel is a feature. It comes out to a feature vector that's about 15,000 or so records or columns. And so depending on how many potato chips we have in our database, that may actually even be more than the sort of repository of images that we have. But certainly it's too many columns to train a model on sort of effectively and efficiently. So we may use principal components analysis to reduce the dimensionality. The way that principal components analysis works is it basically is a matrix decomposition technique that tries to create a lower dimensional projection of the input data. So we may be taking those 15,000 and trying to compress it into say a set of 20 vectors that makes up or accounts for about 99% of the variation within the total 15,000. And the idea is it's a technique for automating feature creation. Again, because we generate our own features, in this instance, PCA is actually going to make our model perform worse, but we're doing it here more for an illustrative purpose than anything else. So here's an example of what it might look like. We actually have 71 features, but we are able to explain the variance in those features, 99% of that variance with just 5 columns. And you can see that the transform values on the right side look absolutely nothing like the original data set on the left side. Okay, so now we're going to create the variables that we're going to use in model building. As I mentioned, we want to test a bunch of different combinations, structures of the model to be able to determine which creates the best error metric on the validation set being a set of data that the model was not trained on. Basically, we're trying to see how well the model can generalize to data that it hasn't seen before in terms of how well it predicts the input variable. So we're going to look at using a random forest regressor from the ensemble module of the scikit-learn library. And we're going to vary 3 parameters. First is the number of trees. Again, if you're not familiar with a random forest model, essentially it's made up of a bunch of decision trees. And this n trees value is going to tell us, the number of trees that we're going to have in our random forest. In this case, we're going to look at a smaller forest that has just 10 trees and a larger forest that has 100 trees. The next parameter that we're going to test is the number of features that are included in each individual tree. So again, if you're not familiar with random forest, it doesn't just build, say, 10 or 100 decision trees off of the same data set. What it's actually going to do is randomly sample a subset of the columns. So in this case, we're going to look at taking a square root of n being the number of features that we pass it, and also log 2 of n. While those actually work, again, because we're using the PCA transformation here, those will work poorly because, as you can imagine, that's going to be a very small number of columns. This is, if we were using all 71 features, these would be common values for us to choose. The final parameter that we're going to vary over is the max depth. And what this is the maximum depth that each individual tree can grow to. So basically the number of splits that it can have along a branch before we force it to stop growing. This is, obviously the deeper that a tree is allowed to grow, sort of the richer the decision set that we get out of it, the more values that we're able to predict. But as you can probably imagine, as we build a tree with more and more and more rules, we're likely to get more overfitting. And again, if you're not familiar with that terminology, if you're sort of newer to machine learning, overfitting is a term that we use when we train a model where it performs incredibly well in the training set, but it is sort of, as the term implies, overfit to that training set and doesn't do a good job generalizing to data that it hasn't seen before. So typically, in any kind of tree-based model, max depth is typically, one of the features that's most often to blame when we see overfitting. Okay, so now we're going to look at doing a grid search over all of these parameters. What you're going to see is in each sort of iteration of this nested loop, we're going to instantiate a random forest regressor modeling object, passing it, one of the different sets of estimators, features, and depth. And again, you can see, as we mentioned before, in certain ensemble models, we're able to build different segments of that model in parallel. And so we're going to take advantage of that here and again pass the n jobs equals -1 parameter. We're then going to fit that model to our training data set, trying to predict that baseline rate. And then after the model's been trained, we're going to use it to predict the rate on our validation set and then calculate a pseudo R squared of that prediction. We're then going to append it to our scoring tracker and check all the results at the end. So at the end here, you can see in a data frame what our pseudo R squared was. As we mentioned, the PCA is kind of unnecessary here, and actually takes out a lot of useful information that was kind of created in those features. So we end up with a fairly poor R-squared, but that's not really the important thing here. You know, we have dummy data, we cut out a lot of our features. The important thing is to kind of understand how this process works. And so here we're going to look at row index number 11, which had the, while not great, still the best R-squared out of all the different combinations that we looked at. And we're going to use that then to predict on our test data set. So here we feed back in the best features, we fit the model to the combination of the training and validation data set, and then we predict on the test data set and calculate our R-squared. And in this case, it turns out it's, while still not great, to be a little bit better than that validation set, and we get an R-squared of about 0.32. I'm going to kind of just jump through these packages, giving just a brief overview of each of them. So we're going to look here at sort of 5 different kind of segments that you should be looking at when you're looking at tools to use in Python. The first is data analysis tools. We used both of these throughout the demo. Numpy adds large array support to Python, and it has a lot of great built-in mathematical functions. Pandas adds data frame support. That was what we're using throughout the modeling and feature engineering process. It's absolutely probably one of the most critical tools that you can have. It's great, I think, if you're first learning Python, you're coming from, say, an R background or a spreadsheet-oriented background. It's very easy to learn. It's very intuitive. SQL Alchemy is a library you'll be using if you're going to be reading and writing from relational database management systems. There's also for other kinds of, say data stores, if you have data in HDFS and Hadoop, you may want to be using something like Spark. There's a PySpark API that's available in Python. We were looking at scikit-learn, which has a lot of the kind of top of the line machine learning algorithms in Python. There's also SciPy and stats models, which provide a lot of other sort of classic kind of scientific and engineering computing, as well as a lot of sort of maybe the statistical tools and linear algebra tools that you may want to use while preparing your modeling or doing some analysis. Matplotlib is kind of the go-to for visualization. I can't speak to it that much. I typically do most of my visualization outside of Python, but it's a fairly robust library, and it has other libraries that are wrappers of it. In terms of deep learning, if you're looking to experiment with that, there's both Theano and TensorFlow. Theano is sort of a more, in my opinion, a more expressive framework. It allows you to be a lot more kind of creative and open-ended with the neural networks that you're building. It's sort of like a complete sandbox. TensorFlow is more of a set of building blocks. I think it's kind of the state-of-the-art, most popular deep learning library right now. It still allows you to build almost anything you could build in TensorFlow with that set of building blocks, and it makes it much more accessible to people who maybe aren't as well versed in the theory of deep learning or neural networks. They have a baseline understanding of the models. They'll be able to create very, very rich and complex neural networks using TensorFlow.